Hi, this is Miss Litton, and this is my wonderful Period 1 AP Bio class. Say hi. Hi. And we had cupcakes today and cookies, and they sang to me, happy birthday, and I spilled my coffee everywhere, but it was a great morning. So we are going to kind of back it up a little bit, and I'll go over the properties of water. So the first thing we want to talk about is valence electrons. And remember, valence electrons are the number of electrons in the what? Outermost energy level. And to make an atom happy, there's two ways to make an atom happy. How can you make them happy? Fill up the shell or get it to 8. Right. Is hydrogen innately a happy atom? No, why? He only has one valence electron. What would he like? One more, so he would like 2. Is oxygen happy? No. How many valence electrons does it have? 6. And it has really high electronegativity. It really wants to have some electrons, so it's very, very happy to share with hydrogen. But when it shares, remember when you share a pair of electrons, what kind of bond is that when you're sharing? Covalent bond. Good. And if you share fair, it's called non-polar covalent, and if you share unfair, it's called polar covalent. What is it if you share so unfairly you rip their electrons away and keep them and they have none? What kind of bond is that? Ionic. Good. All right. So in this situation, oxygen does share with hydrogen, but it keeps the electrons closer to the oxygen, and as a result, hydrogen has a partial what charge? Positive. And this hydrogen has a partial positive, and this oxygen has a what? Partial negative. So when you throw all of those water molecules together in a container, then those water molecules naturally arrange themselves so that the positives, partial positive charges, are attracted to the partial negatives. And when they do that, and here I'm just going to back up here so we can look at this. When we looked at, we can see how hydrogen and oxygen are sharing and the arrangement of that bond. And we reviewed also the 3 important inorganic molecules. Slate, tell Blue. Did you just go, Slate? Yeah. Here we go. Slate, you name the 3 important inorganic molecules that are here on the board for you. And Blue, you tell them the 4 important organic molecules that we're going to be learning about later today. Go. Okay, so come back to me. The 4 important organic molecules. 4 important organic molecules are lipids, nucleic acids, carbohydrates, proteins. Perfect. And the 3 important inorganic molecules are oxygen, carbon dioxide, water. And water. Since most of your body is made out of that very important inorganic molecule, water, it's really important how it reacts with other water molecules. So if we look here at a water molecule, and I am now going to spill some water, much like I spilled my coffee. Are we okay? Yeah, I agree. All right, so when you have these water molecules arranged, then what you're going to start to see is you have this partially negative charge being attracted to this partially positive charge right here. And what you will get between them, oh darn it, that was the one, is right here is a bond right there. And that bond is called a what kind of bond? What's that bond? This is a hydrogen bond. Do not get confused. There's a bond right here between oxygen and hydrogen and a bond right here between this, and that one is called a what? Polar covalent bond. Okay? In the polar covalent bond, they're actually sharing a pair of electrons very unfairly. But as a result of that unfair share and the partial charges, then you can have these hydrogen bonds. And over here, you can have some more hydrogen bonds between this water molecule and that water molecule, and so forth. Oh, not that bond. Go away. Okay, bond. There, we'll go over the top of you. You can have another hydrogen bond, and then you can have another hydrogen bond, and you can have another hydrogen bond, and you can have another hydrogen bond. And all of this holds the water molecules together. And that's called cohesion, because they're all stuck together. This is why if you jump into your pool like this and go smack, what is that called? Belly flop. That's why it's so painful. Okay, because all the water molecules, for an instance, are hanging on to each other and going, I got you, brother. Okay, and then you go through. And this is why if you take a cup of water and you fill it up, you can fill it up just a little over the rim, because they're like, no, they're like firemen. I will not let you go. Okay, and they hang on to each other. And this is why it takes a while for water to boil, because all the water molecules are like, no, my family. Okay, and then finally it has enough energy that it has a high heat of vaporization before it evaporates. So all of these things, when you have another molecule thrown into water, let's see if I have that. I do, it's right here. When you have, this is NaCl, what's that? Salt. I didn't want to be that. So when you throw out a bunch of water molecules right here around the salt, talk about how they're going to arrange themselves with your bio buddy. Go ahead. How are they going to arrange themselves? Okay, so what's the charge on sodium? Positive. So which part of the water molecule is going to be attracted to it? The oxygen. Okay, so all the oxygens are going to be attracted here so that it can form those hydrogen bonds. So it can form those hydrogen bonds between the sodium and the oxygen. And then over here, all of these, which part is going to be attracted to it? The hydrogen. Now, water that is in this state like this is called bound water, because it's hooked up with another substance. It could be another polar molecule, or it could be an ion like this, and it is connected to it. And most water in your cells is bound water. It's already hooked up with something else. But you can see hydrogen bonds with other things, not just with water. And when we look at nitrogenous bases in DNA, adenine with thymine and guanine with cytosine, these dash marks here, those are those hydrogen bonds. Okay, now let me ask you this. Where do you think there are more problems due to, let's say, UV exposure and breaking of those hydrogen bonds between adenine and thymine or guanine and cytosine? Why? They only have 2 hydrogen bonds, and between guanine and cytosine there are 3. Sometimes, like radiation, can make one adenine and thymine break and another adenine and thymine break, and then the 2 thymines hook up. It's called the thymine dimer, and that causes problems. But that has to do with hydrogen bonds. The shape of proteins. We're going to talk about the structure of protein. The folding pattern is all dependent on these kind of interactions like hydrogen bonds. And what we will grow to know and love is that the functionality of that protein, may it be an enzyme or an antibody, is completely dependent upon the structure. Structure makes function. It's kind of like you have keys, right? But keys only work in certain what? Yeah, keyholes, certain locks. And if you do anything, if you took your hammer and you're like, I'm going to make this key better, okay, and you changed it, and then you tried to put it in that lock, it wouldn't work anymore. It wouldn't be able to do its job. And proteins, which are significant for life functioning and cellular metabolism, if their shape changes, then their functionality changes. And when we look at things like water, water goes in there and binds onto certain molecules, and bound water makes molecules act differently. So we're going to talk about the importance of that as we move through, and some other properties of water. So on your notes, go to water, water, water. Living things are 70 to 90% water. Now, when you did your labs last year, do you remember when you had a graduated cylinder and let's say you had to measure a certain amount of water? Do you remember what that was called right there? Meniscus. And if you had a glass graduated cylinder, that meniscus would be real distinct. And the reason is that water can bind to something like glass really well, and it starts to creep up the side of it, and that's what creates that meniscus. But if it's plastic, you don't see that meniscus. It goes straight across because there's nothing for the water molecule. There's not another polar molecule for it to bind onto. Okay? And when we go through, that's what you'll see on the notes where it says, and with other polar or charged molecules. And when water hooks up with another substance that's not water, but it's a polar molecule, so it can connect to it, like glass, to create that meniscus, that's called adhesion. So cohesion is water to water, adhesion is to another polar surface. So this is what it would look like when it's just pure distilled water. Here are some of the properties that we're going to talk about. One property is that oxygen is a gas and hydrogen is a gas, but when they're together, they form a liquid water at room temperature. They really should both be gases, but what keeps them in the liquid state? Because all of them are hanging on to each other, and that's why you have it as a liquid. It's a very good solvent as long as you're a polar or charged molecule. It's a great solvent. What doesn't dissolve well in water? Oils. And the reason why is they're non-polar, and so they don't mix well, and we'll be talking about that. They can fill up vessels and shapes. They can gain and lose heat very slowly. This is like the overview of the whole thing we're going to discuss. And the reason is, where do you think temperature is more moderate? Where I live in Camarillo or here in Oak Park? Camarillo. If you look at the annual weather, it's like 72 year round. Here in Oak Park, super hot in the summer and super cold in the winter. And the reason is you do not have the mediating effects of the ocean. Camarillo, it's open through the Oxnard Plains all the way out to the ocean. But what's between you and the ocean here in Oak Park? The mountains. But see, what happens in Camarillo, even if it's a really hot day, is as the sun's energy comes in, it hits the water, and the water can absorb it. It can yeah, we got it. More, okay? And it'll hold all of that energy and all of those hydrogen bonds, and then in the nighttime, when it cools, it'll re-radiate that energy back out. So it keeps the temperature pretty constant. But here we don't have, between us and the ocean is a big barrier of the Santa Monica Mountains. So here, when it's hot, the dirt's like, fine, I'll take it, that's it, done. And then it re-radiates it back out for you so you can feel it, yay. Okay, and then the same thing when it's cold. You don't have something to hang on to that energy for you, and that's why when your hot is hot, your cold is cold. High heat of vaporization, this is critical, because if water vaporized really quickly, that would be bad for our internal body structures, right? And so it takes a lot of energy before it will actually evaporate. And then it is less dense when frozen. We'll talk about the significance of that. You might already know that. We'll work our way through. But it protects life in lakes. So take a look at this picture. Just like one of those pictures where you make your eyes go weird. What are you actually looking at? What's the color? Yeah, the color is actually the ocean, and the white part is land. Do you see it now? You got it? It's like sideways. Okay, Slate, explain, what is this picture demonstrating? Go ahead, go over it with them. If you look at your notes, the way I listed it out is I listed an attribute above, and then below I gave the biobeny of that attribute. Do you see that? You with me? So if you look at your notes, number 1, there's a high heat capacity. Hydrogen bonds can hold a great deal of energy. Then look below, biological benefits applied. Do I have that for you?
It's to the side.
Oh, to the side. Sorry, I couldn't remember how I had it in mind. So to the side, it protects organisms from what? Did I give you this in your notes? Oh, well, let me give it to you now. I didn't highlight it. Protects organisms from rapid temperature changes and helps them maintain homeostasis. Protects organisms from rapid temperature changes. Oh, okay, I see. I didn't give you anything. Yeah. Protects organisms from rapid temperature changes and helps them maintain homeostasis. That's the biobeny of high heat capacity.
Could you restate that?
Yes. And beta, help alpha out so I don't have to say it too many times. Protects organisms from rapid temperature changes and helps them maintain homeostasis. Okay, take a look at this diagram. Blue, you explain this diagram. Go ahead. Okay. Okay, I'm jumping in. High heat of vaporization. This is where you see a big jump. It takes a lot of calories before, a lot of energy before it goes from a liquid to a gas. High heat of vaporization. It takes a great deal of energy before water will evaporate. H bonds hold the water together as a liquid. H bonds hold the water together as a liquid. And the biobeny for that, applying it, it moderates the Earth's surface temperature. Moderates the Earth's surface temperature. Or temperatures, make that plural. Moderates the Earth's surface temperatures. Beta, you should be helping out. Permits living systems to exist. Moderates the Earth's surface temperatures, permits living systems to exist. Okay, number 3, solvent. There are 2 words here to learn, hydrophilic and hydrophobic. And here they are. And when you talk about hydrophilic and hydrophobic, if somebody has a phobia, they are what? Scared. Hydro is referring to water. So hydrophobic, you're afraid of water. Hydrophilic, philic, you what? Love water. So that's where those words come from. So organic molecules will behave in water differently depending if they're hydrophilic or hydrophobic. And if you are polar or charged, you're hydrophilic because water can arrange itself around you. If you are a non-polar molecule like a fat, with long fatty acid chains of single-bound carbon, hydrogen, and carbon sharing fair, then water comes up to you and it's like, you want this? I want this. This, and it's like, whatever. And so water can't make any connections with you, but it can make connections with itself. So it's like, you don't want me, another water molecule does. And so they will get together, and so all the non-polar substances will get together, and all the polar substances will get together, and that's why you have to shake your Italian dressing. Now, there are things called emulsifiers, right? Because your ranch dressing, that has fat in it, right? And it's delicious. But your ranch dressing, it doesn't separate out like your Italian, like your balsamic, your vinaigrettes, well, the oil and the water. And that's because there are emulsifiers in there, where in the fats themselves, other molecules are mixed in with the fat that are actually polar. So they're taking a non-polar substance and lining it with polar items, and that's how it will just all be thick and creamy together. Your soaps and suds, all your, to clean yourself are emulsifiers, breaking up the fat into smaller chunks so that it can wash off your body and leave your body, because otherwise the water would just run off your body, right? So the soap helps emulsify it. Dawn dishwashing soap, if you've ever seen a commercial for it, I make no money from Dawn dishwashing soap, but I will tell you, it works markedly better than any other detergent that I use to wash dishes. I can totally tell the difference. You don't know, but I've been doing dishes for a very long time, okay? And it cuts the oil. It's a better emulsifier. It's more expensive, but it's a better emulsifier than a cheaper detergent. So the chemistry in it is different. You can tell by it the way you get your outcome. So when I tell you it is a good solvent, it is, unless you're a hydrophobic substance. So solvent, hydrophilic, loving, hydrophobic, fearing molecules act differently in water. A solvent can have dissolved substance in it, and that would be called a solute. On your BioBenny, water can arrange itself around polar/charged molecules. Water can arrange itself around polar/charged molecules. What's a major liquid that runs through your body? Blood. Okay? Now, your blood has formed elements in it, and it has dissolved element, like the fluid portion of your blood. The fluid portion of your blood is called what? Starts with a P. Plasma. And within that plasma, you have gases, you have nutrients, you have salts, you have waste, you have hormones, you have vitamins that are all dissolved into your plasma. And some of those things are fatty substances that have to stay dissolved, okay, within your blood. If they separated, you'd have to be like shaking your arms all the time like salad dressing, right? You would cause problems. So there are emulsifiers on little proteins that are polar that get attached to fat so that it can keep passing through your system. So water is a great emulsifier. Blood plasma is mostly water. So that works out for our benefit. So on solvent, BioBenny, water can arrange itself around polar charged molecules. Blood plasma is mostly water. Blood plasma is mostly water. Okay, so next thing to talk about is we depend on autotrophs for what? What do we depend on autotrophs for? Food and what else? Oxygen. Turn down your phone. Food and oxygen. Now here's the deal. Trees, some are low-growing trees, some are very tall trees. The water, where does the water come from for those trees to stay alive? From the roots. It's got to go up against what? Gravity. Gravity says go down, okay? But yet that water goes up to the very, very top of the trees. Now that's powered by, do you remember, I think we talked about this in fossil a little bit, transpiration. Evaporation of water out opens stomata. So water will evaporate, but still, to explain how water can go up, how many of you have been to the giant redwoods? They're super tall, right? You drive cars through them, not anymore. I think they stopped you from doing that, but you're like, so tall, okay? How does that water get up there? That's like, so tall. It's a cohesion and adhesion, and here's how it works. One water molecule is connected to another water molecule, which is connected to another water molecule, which is connected to what? It's like they're all holding hands. Okay? What's holding them together? It's called cohesion, but what's actually holding them together? Hydrogen bonds. Okay? On top of that, the part of a plant that transports water, it starts with an X. Does anybody? Xylem. Yeah. Xylem has a polar surface to it. So not only are the water molecules holding on to each other, they're also doing adhesion on the xylem walls. So they're like, if you went to like some circus where one person is standing on top of another, right? Like on their shed standing. It's like, man, I'll fall over. But they can hang on. All the water molecules are hanging onto the xylem walls and onto each other. So that's the state of things. And then you have these openings in your leaves called stomata. And so what happens is you have this long column of water that extends from the leaves all the way down to the roots at the very, very bottom, and it's a continuous column. So as the sun shines on this water molecule right here, he's getting more and more energy, and he's like, I think I'm going to evaporate now. I have enough, and he starts to go, but when he goes, what is he doing? He's pulling them all out. He's pulling all of them. As he evaporates out, he pulls all of them up. And that is called transpiration. Does that make sense to you?
Yeah.
What? When does it start?
9.
When is starting?
Wait, but did you get that?
No, I have boxes. Yeah, it's starting to get partially. Okay, I have 3 boxes. Yeah. We can live stream it. Is that what we're doing so far? I think. Where did he go to see that? My sister's university. Oh. All right, keep going. Did you know at LA Unified they have to shelter in place? You know, like if there was a storm outside, they have to shelter in place, like because they're afraid the children will look at all grade levels up at the sun.
Yeah, for elementary school. No, for like elementary school. Are they just gonna like kindergartners know outside? So that will never get to see it.
No, they will just live stream. Okay, wait. So let me get through this. Let me get through this water, and then we can start to look at things. Okay, come back to me. So, its transpiration is the power behind it, the evaporation, but you would have to have the adhesion and the cohesion to make it work, and also there's something called tension, and it has to do with water potential. I will teach you that later, but water always goes from a higher water potential to a lower, and there's higher water potential in the roots and lower water potential in the leaves, so it's that also is helping it to move along. So on your notes where it says, number 4, cohesive and adhesive, bonds with itself and to other polar surfaces. Bonds with itself and to other polar surfaces. And then your number 4, biobeny, allows water to move up through trees. Allows water to move up through trees. And I'm going to give you 4 words on that. Transpiration allows water to move up through trees. Transpiration, adhesion, cohesion, and tension. Adhesion, cohesion, and tension. Okay, and number 5 is high surface tension. I don't know if you can see this, if this conveys it, but do you see how the water strider, it's like it's sitting in divots in the water? And that's because all those water molecules are hanging on to each other, and it's actually indenting the water. Okay, now, if on an essay, I ask you to give me the properties of water, like name and describe 3 different properties of water, why they have that property, and a biological benefit of that property, listen to me right now. Don't pick this one. This is like a little interesting thing, like, hey, and look at the water strider, okay? So you would not spend time using that as a key point of the biological benefits of water. Do you understand? Water striders can move. Okay, great. Okay, I'm just giving you an example here of water striders. Okay, so your biological benefit, I just wrote water striders like it. So number 5 was high surface tension, think belly flop, and then I put water striders like it. You're not going to pick that one. And then the last one is when water molecules are in a liquid state, do they have more or less energy than when they're frozen? More. More or less kinetic energy? More. Kinetic energy is energy of motion. So water molecules, it's like when they form those hydrogen bonds, they're not like faithful in them, okay? When they're in a liquid state, because they're like, yeah, okay, I'm with you, okay, with you, all right, fine, okay, yay. And the water molecules move around, they're shifting all their little hydrogen bonds. But as they lose energy because it's colder, they start to slow down and make a commitment, okay? And all those commitments have equal distance and equal space. So as a result of that, when you have frozen water, you can see everything is perfectly regimented out, thinking about bond angles, forming hydrogen bonds, and you have a lot of space. But in liquid water, they're moving around more, and so liquid water is more dense than frozen water, or conversely, frozen water is less dense than liquid water. As a result, ice does what? Floats. Even though it's a solid on a liquid, it floats because it's less dense. So this is hugely important if you think about bodies of water like lakes and think about winter. And what happens is the coldest part of the lake is oftentimes at the very bottom of the lake. It starts to make ice, and that ice slowly floats up to the surface with other bits of ice and other bits of ice, and then it becomes a solid frozen insulating layer, which is good, because if it wasn't that way, if ice was more dense than liquid water, it would freeze solid from the bottom of the pond all the way up, right? Because it would go to the bottom of the lake. And then what would happen to all the life in the lake? It would die. Yeah. So on your notes, frozen water is less dense than liquid water. As water approaches freezing, the hydrogen bonds all become equal distance, expanding, becoming more uniform. Ice is less dense than liquid water. You only had to put in the less dense there, right? The biological benefit, ice acts as insulation layer. Ice acts as an insulation layer on a body of water, protecting the life below. Protecting the life below. Okay, and the last bit on this notes are acids and bases. And when water, very little of this will do this in water, but when water dissociates, it releases hydrogen and hydroxide ions. Normally very few molecules will actually dissociate, but some do. An acid, if you look at the scale, an acid, is it a low number or a high number? Low number. Look at the coloring on this. Do you see the red and the blue colors? What does the red stand for, do you think? Amount, can you read it right here? Yes, exactly. It's the amount of hydrogen is the red. Whereas the blue is the amount of hydroxide ions. So you can see when it's acidic, it's thick, thick red, thinner, 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 hardly any, and just the opposite for hydroxide ions. Okay, your lowest number here for an acid is 0, your highest one is 14. When you look at a pH scale, yes, this is just 0, 1, 2, 3, 4, I got that. It's one change in number. But when you go from a pH of 4 down to a pH of 3, it is a 10-fold difference in increase of hydrogen ions. And so therefore, if you go from 4 all the way down to 2, it's 10 times and 10 times, so it's a difference of 100. And if you went 4 all the way down to 1, it would be 1,000. Okay, so because of that. So on your notes, you have acid. When put in water, it releases hydrogen ions. It releases hydrogen ions. And a base is when it's put in water, it releases hydroxide ions. You already have that. The pH scale measures the amount of hydrogen ions. A low pH has high hydrogen ions. High hydrogen ions. each change in value is 10 times the concentration. And I gave you everything there. I'm trying to hurry because of the eclipse. Buffers. Oh, acid, rain, bad. Buffers. It is a chemical or a combination of chemicals that keeps pH within normal limits. Keeps pH within normal limits. They work by taking up excess ions. It is a chemical or a combination of chemicals that keeps pH within normal limits. They work by taking up excess ions. The biological benefits is you have a normal blood pH. Normal blood pH. Okay, I'm going to do the review questions in our review. Okay, 2 things what I want to have happen. First, we need to have a realization that we should have already been halfway through chapter 3 by today. So this is a worry to me because we took a long time getting our labs done and completed. Okay, and then we had to finish up the water, and then we're finishing a little bit early because of the eclipse. So we'll have some work to move a little bit faster next time. But, you know, since this only happens every 100 years or so, I thought, you know, we might as well start looking at things. This is what I want you to do. 2 things. You can pull up, we don't want everybody to live stream, otherwise it'll take too much data, but I'll pull it up here on my computer. If somebody wants to get that going, or a good website, tell me and we'll pull that up. Go ahead, go get it on my computer. Talent for everything. For your blog today, because we have 15 minutes left. For your blog today, I want you to blog on 2 things. One thing you learned, and 1 thing about the eclipse. Note the eclipse. And I have 3 boxes that we can share. So let me show you how they work. There is tin foil here on the end with a hole poked into it. Don't screw the hole up. Face this towards the sun, but don't look at the sun, right? And then on the opposite side of the tinfoil side, there is a piece of white paper in here, and you look at it from the side, and you can see it on the white paper on the far side, okay? So you're like, go like this, but don't look at the sun, just be like, is the sun shining on it? You can put your hand up and see where the shadow is. That's another way to see where the sun is coming from without actually looking at it. And then shine it on there. In fact, you might even try this simple task of making a very tiny space with your hands and see if you can see it on the sidewalk. It's a very easy eclipse box to make with your own hands. Okay, so find your blog. We're going to get it streaming up here, and I have 3 of them. Some people go and check and see if you can see it. NASA. Don't look at the sun. Do you know where my internet is here? Here, I'll start this. Oh, and hope you're having a good day. Okay, then.